In the autumn of 1837, Charles Darwin began an experiment in his garden at Mare Hall in Staffordshire that he would not publish conclusions from for another 44 years. He was not studying evolution. He was studying earthworms. Specifically, he was studying the rate at which a population of earthworms could bury a layer of chalk fragments spread across the surface of a field, pulling organic matter downward, processing it through their bodies, and depositing it as transformed soil. What he found over those 4 decades of meticulous observation was not a curiosity. It was a mechanism, a biological engine running silently beneath every productive piece of ground on Earth, converting organic waste into the most nutritionally complete plant food that chemistry has ever attempted to replicate, and never fully succeeded. Darwin published his findings in 1881, a year before his death, in a book titled The Formation of Vegetable Mold Through the Action of Worms. It was, unexpectedly, his best-selling work during his lifetime. Farmers recognized immediately what the scientific establishment took decades to acknowledge, that the earthworm was not incidental to soil fertility. It was the mechanism of it. Ancient agriculturalists in Mesopotamia, in the river valleys of India, in the raised field systems of Mesoamerica, had understood this through observation long before Darwin gave it language. Cleopatra reportedly declared the earthworm sacred and prohibited its removal from Egyptian soil under penalty of death. The pharaohs understood something the synthetic fertilizer industry has spent a century asking you to forget. In 2023, the global synthetic fertilizer market was valued at over $200 billion. That number is not a measure of agricultural success. It is a measure of how completely the industry has managed to substitute itself for a process the soil was already performing for free. Synthetic nitrogen, phosphorus, and potassium, the NPK triumvirate printed on every bag of commercial fertilizer, are not plant food in any complete sense. They are a narrow chemical signal that triggers plant uptake responses without providing the hormonal compounds, the microbial metabolites, the humic and fulvic acids, or the enzymatic activity that living soil biology delivers alongside its nutrient release. A plant fed on synthetic NPK is the nutritional equivalent of a person surviving on glucose drips, technically alive, measurably growing, but operating without the biological complexity that makes the system resilient. The deeper damage is structural. Synthetic fertilizer inputs bypass the soil's biological nutrient cycling systems entirely. When plants receive soluble nitrogen and phosphorus directly, the microbial populations responsible for mineralizing organic matter, the bacteria, fungi, and protozoa that constitute the soil food web, have no function and no carbon energy source to sustain themselves. They decline. Over successive seasons of synthetic input dependency, the soil's self-sustaining biological infrastructure atrophies. The organic matter fraction drops. The microbial biomass contracts. The soil's water retention capacity decreases, its aggregate structure collapses, and its capacity to produce fertility without external input approaches zero. This is not a side effect. It is the business model. Soil that has been rendered biologically inert by decades of synthetic input dependency cannot recover its fertility without continued synthetic input. The farmer who entered the system voluntarily has, over 10 to 15 seasons, been structurally locked into it. The industry does not need to suppress the knowledge of what earthworms do. It simply needs the soil to forget how to support them. The mechanism by which earthworms regenerate soil fertility operates across 4 simultaneous biological and physical processes, each compounding the effects of the others. The first is mechanical fragmentation. As an earthworm ingests soil and organic material, it physically reduces particle size, breaking down leaf litter, decomposing plant matter, and mineral soil aggregates into fragments with vastly greater total surface area than the source material. Surface area is the variable that governs microbial colonization rate. A fragmented particle hosts exponentially more bacterial and fungal attachment sites than an intact one. The earthworm is, in effect, a living preprocessor that prepares organic material for the microbial communities that complete the decomposition process. The second process is gut inoculation. The earthworm's digestive tract is a microbial incubation chamber. Bacteria and fungi ingested with soil material are exposed to gut conditions, specific pH, moisture, and enzymatic chemistry that selectively amplify beneficial microbial populations before they are deposited in the casting. Research on earthworm castings consistently shows microbial biomass 5 to 10 times higher than surrounding bulk soil, with disproportionate representation of plant growth promoting bacterial genera including Azotobacter, Nitrosomonas, and Pseudomonas. The third mechanism is nutrient transformation. Raw organic material, kitchen scraps, garden waste, decomposing plant matter, contains nutrients locked in complex organic molecular structures that plant roots cannot access directly. The earthworm's digestive process mineralizes these compounds, converting organic nitrogen into plant-available ammonium, organic phosphorus into soluble orthophosphate, and complex carbon chains into the humic and fulvic acids that chelate micronutrients and make them available across the root membrane. A kilogram of earthworm castings contains more plant-available nitrogen, phosphorus, and potassium than a kilogram of commercial compost, and does so in a slow-release form that resists leaching through rainfall. The fourth mechanism is structural improvement. Earthworm burrows create a network of macropores through the soil profile vertical channels that improve drainage, aeration, and root penetration simultaneously. A soil with active earthworm populations has hydraulic conductivity 2 to 10 times higher than comparable soil without them, meaning it absorbs rainfall faster, holds it longer, and delivers it more evenly to the root zone. In drought conditions, this difference is the difference between crop survival and crop failure. A buried pipe loaded with kitchen waste and positioned in your garden activates all four of these processes simultaneously, continuously, within a 30-centimeter radius of the installation point, delivering fertility directly into the root zone of the plants you want to feed, without dilution, without runoff, without any energy input from you beyond the organic material you were going to discard anyway. A 1 kilogram bag of synthetic NPK fertilizer retails between $8 and $15 and produces 1 to 3 applications before exhaustion. It does not improve your soil. It does not increase your soil's capacity to produce future fertility. Each application is complete in itself. The soil is no more capable after the application than before it. You pay again next season, every season, indefinitely. The worm tower costs between $0 and $12 to build from materials most households already have or can source freely. It operates continuously for the life of your garden. It improves soil biology with every passing week. Its fertility output increases over time as the worm population and microbial community it supports expand. The return on that $12 investment compounds annually, not depreciates. Source a length of PVC pipe, 10 to 15 centimeters in diameter, 60 centimeters long. Drill holes across the lower 2/3 of the pipe at 3 to 5 centimeter intervals using a 1 centimeter drill bit. These perforations are the interface between the tower and the surrounding soil, the exit point for worm castings, microbial inoculants, and liquid fertility as it migrates outward into the root zone. Dig a hole 40 centimeters deep in your garden bed, positioned centrally among the plants you intend to feed. Set the perforated section of the pipe into the hole, leaving 20 centimeters above the soil surface. Backfill around the pipe and firm the soil. Place a loose cap, a terracotta pot saucer, a piece of tile, a flat stone, over the top opening to exclude flies and retain moisture. Begin loading the tower with kitchen scraps, vegetable peelings, fruit waste, coffee grounds, crushed eggshells, tea leaves. Avoid meat, dairy, and cooked fats in the initial establishment phase. Add a small handful of garden soil or finished compost with the first load to introduce the microbial and worm populations that will colonize the tower. Water lightly after each loading. Within 2 to 4 weeks, native earthworms from the surrounding soil will locate the organic material through chemoreception and begin entering the tower through the perforations. No purchased worms are required. The system self-populates. Once established, load the tower with kitchen waste 2 to 3 times per week. The surrounding soil within a half-meter radius will begin showing measurable fertility improvement within a single growing season. Darwin spent 44 years watching earthworms work before he published his conclusions. Not because the evidence was unclear, it was obvious within the first decade, but because he understood that what he was documenting had implications that reached far beyond soil science. A garden that feeds itself. A fertility system that strengthens with age instead of depleting. A biological infrastructure that requires nothing from you except the scraps you were discarding. The synthetic fertilizer industry built a $200 billion market on the premise that the soil needs their chemistry to function. What it actually needs is the biology it has always carried, biology that a buried pipe and a handful of kitchen waste can restore in a single season. The earthworm was doing this work before the first human planted the first seed. It has been waiting for you to get out of the way.